So you've gone over IMFs at some point in your life, like hydrogen bonds and London dispersion forces and stuff like that.
Yes.
All right, cool. So when you're making a solution of any kind, you got two jobs. You have to actually tear the water molecules apart from each other. So that takes energy to bust those things apart. And you also have to tear the salt crystals apart from each other. So that purple and green is sodium chloride. So we have three steps kind of in making a solution. First, tear everything apart. And then, so that's step one and step two. And then step three is kind of like let everything come back together. So once we pull the sodium and chloride away from each other, and once we pull the waters away from each other, then we can start to set up those water molecules facing the chloride ion and the water molecules facing the sodium ion. And we call that an ion dipole force, because water is a dipole and ions are, well, ions. So it takes energy to break everything apart. But then as everything kind of comes back together, energy is released. So that's why some things, when you dissolve them, they get warmer. And some things, when you dissolve them, they get cooler based on how much energy gets absorbed to break everything apart and how much energy gets released as you kind of let everything settle back together and form those intermolecular forces. So between those two, between vitamin A and vitamin C, which vitamin do you think might be more soluble in water if I try to dissolve it in water?
I'm not sure. Maybe vitamin C.
Of course, vitamin C. You're right. So see those blue OHs hanging off of it?
Right.
Yeah. So those are places where the vitamin C molecule can hydrogen bond to water. So at those parts of the molecule, it's very, very, very polar. And whereas in the vitamin A, most of the vitamin A molecule isn't polar at all. There's only that one little end. So vitamin C, you could totally dissolve in water. You find it in fruit juice and lots of other things. Vitamin A is dissolved in fat. So vitamin A, oftentimes you'll find in liver and some other things because it's really only soluble in, say, non-polar things like fat or oil.
Okay, so polar molecules, they dissolve in water because, like, water is polar. Is that why?
That's right. Polar likes to dissolve other polar stuff, and non-polar stuff likes to dissolve other non-polar stuff. So if you had a greasy stain on something, water doesn't help. But if you used a non-polar solvent, even something like gasoline, it would take the grease out. Now, your clothes would smell like gasoline and be flammable, yeah, but it would take the grease out, right?
Right.
So concentration, when we talk about, we made a solution of some kind, it's always expressed in moles per liter. So molarity is moles per liter. And you have to remember that if I took a beaker full of solution and heated it up, it would actually expand. And if I cooled it down, it would actually shrink down some. So molarity can change with temperature. So if we took a 1 molar solution, it'd be 1 mole and 1 liter of solution. If I heated that up, it would still be 1 mole, but now it would be in more than 1 liter of solution. So sometimes they'll try to trick you and say, which of the following things will change with temperature? Like mass, well, that doesn't change. Length, well, that doesn't really change. How about molarity? Well, yeah, molarity might change with temperature. So when you go to make a solution, it's very important that you pick the right glassware. So have you seen all these things at some point in your laboratory experience?
Yes, I think so.
That's great. So a pipette is just a little tiny pipe. And a burette is a glass thingy with a valve at the bottom. So you fill it up and then you dispense out of the bottom of the burette. And a graduated cylinder, I know you've seen before. And then a volumetric flask is one of those flasks that's only got one line. And that one line is going to be exactly like 1,000 milliliters or exactly 250 milliliters. So we never want to use a beaker or anything like that. We want to use very exact glassware when we're trying to make a solution. So you probably have seen this calculation at some point, probably in chemistry last year. Does that look familiar at all to you?
Yes, yes, it does.
Okay, cool. Something very commonly seen on the AP exam, especially in the multiple choice part. If you do, I like the MCVC equals MDVD because the C and the D means concentrated and dilute. The 1 and the 2, I find that sometimes my students kind of get confused and they'll drop the wrong one in place. So the idea here is we just need to know how much concentrated solution do we start with, and then we add a bunch of water and we dilute it, and we can create a solution of whatever kind we want. So here's an example. If I took 1 milliliter of a 1 molar solution and I added 9 mils of water to it, that's a total volume of 10 mils. So I can plug in like M1V1. So I can plug in 1 milliliter and 1 molar is equal to M2V2. My new volume is 10 milliliters. And what we find is the molarity went down to 0.10. So the math is really just plug and chug. Plug in the concentrated one, plug in what you know about the dilute one, and solve for the thing you're not really looking for. I mean, solve for the thing you're looking for. Does that kind of make sense?
Yes. So like, you do the molar like dilute and molar concentrated. Does it matter like between the 1 and the 2, like on the AP exam, I guess? Like,
no,
it
doesn't matter. Most people go with 1 and 2, but for example, in this problem over here that I just showed you, some people will confuse it and they'll say, oh, volume 1 is 10 milliliters and volume 2 is 1 milliliter. They'll kind of switch the numbers.
Right. Okay.
And that's only because the more concentrated one is 1 molar. So I would call that MC. And VD would be the volume, VC would be the volume of the concentrated 1 milliliter. And then once I add a bunch of water to it, that's dilute. So I would call VD 10 milliliters. It just kind of helps some students track what is the right answer there, how to plug it in.
Okay.
So the other thing that's important, and you've probably made a solution at some point in your life, even at home, the step is pretty easy. You add the concentrated liquid, then you pour in the water, and you pour in enough water to bring it to the final mark. Like for instance, you wouldn't add 10 milliliters of water and then 1 milliliter of the concentrate, because now you don't have 10 milliliters, now you really have 11 milliliters, and that wouldn't be helpful. So whenever you're making a solution, you put the concentrated liquid in there, and then you pour water in up until it gets to that mark, and boom, you're done. So here's a question I'm going to let you and I kind of talk through. We can kind of figure out how to work this.
All right.
So this is a dilution problem. So what would be MC, the concentrate, and VC, the concentrate, and what would be MD, and what would be VD?
Okay, so I guess the molarity concentrate would be the 4M.
There you go. That's right.
I
So
guess
what would be the VC, the volume of the concentrate?
The 25 milliliters.
Nice, good job.
And then yeah, the like the VD would be the 100 milliliters.
Okay, so here's the thing where you got to watch. Is the new volume 100?
Oh, it'd be 125.
Right, that's where they're trying to get you, right? So the volume of the dilute would be 125 milliliters. And then you could find the concentration.
Okay, let me just set it up.
Right, there you go. So the setup is going to be the 4 molar times the 25 milliliters is equal to the molarity that we're looking for times 125 milliliters.
Well, okay, I think I messed it up. I have like 0.7 milliliters, and I know that's not right.
Okay, so let's do this. See. Oh, that's right, Matt. There is no whiteboard here, is there?
There's not.
Okay.
Do you have a? Do you have a tab? Are you on a tablet?
I've got a Wacom thing, so
You could just pull up the Google Slides presentation, I guess, and share your screen.
so it'd be 4 molar is equal to the molarity that we're looking for times 125 milliliters, which means that the 100 is equal to the molarity that we're looking for divided by the 125. So does that look reasonable?
Yes.
Okay. So what's 100 divided by 125?
0.8.
Okay, 0.8. Now, so let's go back to what I had going on. Right. So is there an answer that's 0.8?
Yes, it's it. I just didn't see the multiple choice.
No, you're fine. You're good. Now, here's the thing. This is a tricky question. This is why I picked this one. Now, calcium chloride, how many chlorines are there for every 1 calcium chloride?
I mean 2.
2, that's right. So if the concentration of calcium chloride is 0.8 of the whole thing, calcium chloride, then what is the chloride ion concentration? Because if you notice there, it says, what is the concentration of the chloride ion?
Oh, so it would be multiplied by 2 because there's 2 moles.
That's right. So there's 2 moles of chloride for every 1 mole of calcium chloride. So the answer wouldn't be actually 0.8. The answer would actually be 1.6.
Right.
So see how they're trying to be tricky because they're like, what's the concentration of the chloride ion? I always tell my kids, you know, if there's 12 people in the room, how many noses are there? And then how many ears are there? Because, you know, sometimes there's 2 of something. So the AP exam is really all about paying attention. The math's not hard, right? It's all about like, oops, I got to read the question, make sure I know what I'm doing.
Right. Okay.
Cool. All right. So here's another type of question that you might see sometimes. Describe the procedure how you would make 100 milliliters of 0.115, whatever that chemical is, right? And what is the appropriate equipment listed below? So I would have had you cross out stuff on a Pear Deck thing. But what piece of equipment up there you're like, no, I don't need to use that?
I guess the 100 milliliter volumetric.
You don't want to use that, or you do want to use that?
Or I would.
Okay, you would. So I was going to ask y'all to draw and mark out a piece of equipment that you think you would not use. So what's a piece of equipment that you probably would not use?
The to in a 50, I don't know what it is, the 2 mole in a 50 milliliter array.
Okay, but you're actually going to need a more concentrated chemical solution in a burette, because think about, you're going to use that to measure out the concentrate.
Okay.
So I look at that eyedropper and I think, I don't need no eyedropper, right? I also look at the beaker. What do you know about beakers and how precise they are? How good are they for doing really accurate things?
Yeah, not very well.
Right. So I would cross out the beaker and the eyedropper. And since I have a volumetric flask, I would probably just use that and not the graduated cylinder, right? So they're asking you to make some assumptions. Now, if you look at this problem, do you know the volume that you're looking for? The volume of the liquid solution you're looking for?
No, but like you could find it by converting the.
Right. Well, it does want you to convert, but see how it says we want you to prepare 100 milliliters of this solution? They're describing to you that is the diluted solution we want to make. So your volume of the diluted would be 100 milliliters, and the molarity of the diluted would be 0.115. And then what is the concentrated solution that you're using to make it? This 2 molar solution here. So this is an example where it's got a question that asks you to think about what's the right piece of equipment and how do I make a solution? But they also want you to be able to do a little bit of that math with that MCVC equals MDVD. Right? And then if you look down at this bottom part, I want you to notice this is a different question, totally different question. They said in order to deliver 10 mils of the iron solution, you get to use one of those pieces of glassware. And then it says, explain why the volumetric flask would be a poor choice to use for delivering the required volume.
Okay. I'm not really sure like how to answer that.
Okay. Well, let's go back and show you what a volumetric flask looks like real quick. So here's a volumetric flask. And how many lines does a volumetric flask have?
Just one.
Just one. So let's think about it for a minute. If you had a 25 milliliter volumetric flask, how would you measure out 10 milliliters of the solution?
Oh, right. So every like thing else has more specific measurements.
Right. Everything else has a bunch of different lines. So sometimes they might say, what's the best piece of equipment? Sometimes they might say, what's the worst piece of equipment? In this particular one, they're saying the 25 milliliter volumetric flask is the worst one. Can you tell me why? And basically you can say it has one line. And since it only has one line and can only measure out 25 milliliters, it would be a bad choice, kind of a thing. So let me jump up. Let's say you had to make something out of a solid. So you don't get a solution. This time you're given a solid. So how would you make that solution? So if I told you 1.25 liters and 0.15 molar, what is molarity equal to again? Do you remember?
It's equal to the, is it moles over liters?
Yes, good job. Yes. So molarity is equal to moles over liters. So do you know the liters and do you know the molarity?
Yes.
Yeah. So you can plug and chug and find the number of moles. So I would start by doing this. I would take the molarity and divide it by, or multiply it by the volume. and I'd get that many moles of that chemical. So when you're using a solid, we then have to figure out how many grams of solid that is, because you'd have to weigh out a certain number of grams. So your next step would be to take that number of moles and you would multiply it by the molar mass. So you'd have to add up the K, the Mn, and the O4. So if you took the number of moles and multiplied it by the molar mass, you would get some answer, 29.6. And you've probably done this before in lab, right? You weighed out something.
Yes.
Yeah. So here's the trick. Would you fill up the volumetric flask with 1.25 liters of water and then add the solid? Or would you add the solid first and then add water?
Okay, I'm not really sure, actually.
All right, so what I want you to imagine is, let's say you put in 1.25 liters of water. When you add a solid to it, for most anything, when you add something to water, it actually makes the water level go up.
Right.
So if you had it right at that 1.25 liters and then you dump solid on top, it's actually going to go above the 1.25 liter line. And you just ruined your solution.
Oh, right, yes.
Right. So the answer is always to put the solid in there, add the water. I like to add about half the amount of water and then shake it or stir it or something. And then once it's dissolved, then I bring it up to the line, that 1.25 liter line with water. But sometimes they'll ask you specifically what's wrong with adding the solid to like 1.25 liters. And you have to be able to say, well, the volume will change. It just won't be right anymore, something like that.
Right. So like on a pre-response question, like you would just say like if you put it in after, the volume will change.
Right. That'd be fun.
Okay.
All right. So do you remember the electromagnetic spectrum? The idea that light it occurs in lots of different ways.
Yes, vaguely though.
Okay, but so we know, you know, the colors of the rainbow: Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And you use, you probably know about ultraviolet light, and you might have had an X-ray at some point. Hopefully you've never had gamma rays, because that's not good for you. You've used some microwaves probably to heat up some food. And then you've got radio waves and television waves. And actually stuck in that television and radio set is also the rays that power your cell phone and power your Wi-Fi signals and those kinds of things. So they're all just different types of light. Some of them are visible and some of them aren't. And we know two things about any wave of light. We can either measure the distance between two waves, and that we call the wavelength, or we can talk about how frequently they hit us. So if you were standing at the beach and waves were hitting you on the beach, we could describe its frequency. I had 3 waves per minute or something like that. So have you ever heard of a hertz before?
Yes.
Yeah. So a hertz is just a per second. So if you ever hear of a radio station and it's like 93.1 on the FM radio, well, that's 93.1 megahertz. That's 93.1 million waves every second. And so when we're talking about wavelength and frequency, we just need to understand that they're inversely related. So if you look at the wavelength, the shorter the wavelength, the more frequently the waves are hitting you. So as one increases the frequency, then the wavelength has to decrease, go down. So we just have that relationship between those two. So there's a calculation that we can do with this. So on your formula sheet that comes with the AP exam, there's a formula that says that C is equal to lambda nu. And you don't have to worry about what lambda and nu. Lambda is that little TP looking thing, and nu is that V thing. They just like to use Greek letters sometimes. But on the AP exam, it tells you exactly what each one of those symbols mean. So if I tell you that the wavelength is 400 nanometers, then we would expect you to change nanometers to meters. And if I give you a known value for the speed of light, because speed of light is a constant, right? It's always 2.998 times 10 to the 8th meters per second. So if I just rearrange the math and solve for V, or frequency, then I can find that the frequency of this light is 7.5 times 10 to the 14th hertz. And a hertz is just an inverse second. It's a per second. So does that kind of remind you of something you've seen before?
Yes.
And does the math seem overly hard, or does that seem doable?
Oh yeah, it does. I just have a question about
Sure.
the conversion. Like the nanometers, is that like a 0.001 meter?
So a nanometer is a micrometer is a millionth of a meter.
Oh wow. Okay.
And a nanometer is a billionth of a meter. So that's why they stuck that 10 to the negative 9th in there. 1 nanometer is equal to 10 to the negative 9th meters. So a nanometer is very, very small, right? And
Right.
that's, as y'all come up on the AP exam, I'm sure that's something your teacher will go over. Those are just reminding you what do prefixes mean, like nano and micro and stuff like that. The other calculation that we can do with light, and those two formulas are right on the formula sheet right together, is we can actually calculate the energy of light. So if I had a given wavelength and frequency of light, then I can find the energy associated with that. So the problem is I've got a photon of light. It's 450 nanometers. So the first step that we're doing is we're changing nanometers to meters. Then I use that equation, C is equal to lambda nu. I plug in the value for C. I plug in the value for the wavelength, and I get a frequency of 6.6 times 10 to the 14th inverse seconds, or hertz. Then you can use the second equation, and you could say E is equal to HV, where E is the energy, H is a constant, just like pi or something like that. It's given to you. It's nothing you need to worry about. And then you also toss in the frequency. V is frequency. So we can throw in those two things, and we can calculate how much energy is actually present in a given photon of light. Does that kind of seem straightforward?
Yes, I think I'll just get it with practice, probably.
Right. And it's just a reminder of what's out there. Now, I did want to take you back to this. Which one of those forms of light do you have the greatest fear of?
Gamma rays, I guess.
Gamma rays. We actually use gamma rays to kill cancer. You can actually aim gamma rays at cancer cells and kill them, right? So that's nothing that we want to use. Now, if you're a fan of the Marvel universe, gamma rays is what they use to turn the Hulk into the Hulk, but he would have been dead because that's just a movie. But if you look, see how the energy goes way up on gamma rays and it's way low down here on radio waves? We know that. So knowing the energy and the wavelength and the frequency of light can be very, very important. So if we looked at all the colors of the rainbow together, you would see red going over to purple. So like kind of all the colors of the rainbow. But when we look at the emission line spectrum of something like hydrogen, what we notice is that the hydrogen only gives off certain colors. And why does it only give off certain colors? And this has to do with electrons. So do you remember that electrons are held in like energy levels?
Right, yeah.
Yeah, right. And then they live also within sublevels. So there's like the 1s and the 2p and those kinds of things. We know that if we energize something, so we give something energy, the electrons will jump up. So go from their ground state, like the 1s, all the way up to a higher energy level. So they absorb energy and jump up. And then when they fall back down to where they started with, fall back down to the ground state, they release energy in the form of light. So when we look and we see, oh, there's a red and a blue and two kind of purples and a whatever that thing on the right is, kind of a light purple, those all correspond to the energies that is present in those electrons jumping. So knowing the wavelengths of light that's given off by something, that tells us something about the electrons. It tells us something about where those electrons are kept, and it tells us something about when they jump from this energy level to that energy level, how much energy is absorbed. So it kind of gives us some insight into where the electrons live in an atom. And have you ever seen one of these with Science in Motion before? Like where you stick the thing in, it glows, like maybe in regular chemistry?
I don't think so, actually.
Right. Have you ever seen a neon light, like at a store or a restaurant or something like that?
Yes.
Yeah, that's all this is. This is a neon light. And as the gas inside gets energized, it gives off light. But it doesn't give off all light. It only gives off light of a certain kind, right? So we can analyze that light by kind of looking at, splitting it up and looking at it, and that tells us something about the atoms. And that's just an example of when those electrons jump up and back, they're giving off certain photons of light. And then if we look at how far the fall is, N is the energy level. So if you jump from the third to the second, that's one kind of light. If you jump from the sixth to the second, that's a bigger fall, right? And it's going to be a different wavelength and thus a different energy. So looking at this, we call this spectroscopy. Looking at the light given off by thing can tell us an awful lot about those atoms and elements and compounds.
Okay, so like, do you have to memorize like the jumps, like the colors, like jumping
Nope.
from 2 to 3?
Nope. There should be very little memorization insofar as the AP exam. You mentioned you were doing like geometry and shapes of things.
Right.
Yeah, those you have to memorize. But this kind of thing, it's just notice that red light here has 656 is unimportant, but that's a bigger wavelength. And up here, it's a shorter wavelength and a greater frequency. So it's not like you have to memorize colors and stuff like that. But you should know in your heart of hearts that red light has less energy than purple light because we're scared of ultraviolet, and that's going to be close to violet. But we're not scared of infrared, which is like heat, right? So you can kind of go, oh, I know red light has less energy than purple light, just kind of from where they are.
Right.
So let me flip over to this. So are you seeing a thing with a big red button and a weird green thing?
Yes.
Okay. So if I take a solution, I'm going to let you pick. What color solution do you want?
The copper sulfate.
Okay, that's the one I had. Great. Okay, so what I want you to notice is if I turn this light on, as the light passes through the liquid, we can measure the amount of light absorbed, right? So what I want you to notice is I'm going to make it more and less concentrated, and you look for what's the connection between absorbance and concentration.
It's a stronger light.
So is it the greater the concentration, the greater the absorbance, or is it flipped the other way around? The greater the concentration, the less the absorbance? Here, I'll take you to this extreme. That's really concentrated. It's really dark.
Okay, so the more it's concentrated, the well, I don't know.
Okay, well, that's not very concentrated, right? It's got a concentration of 34, and the absorbance is 0.32. If I make it very concentrated, make it 200, then the absorbance comes up to 1.92.
Okay, so just the more it's concentrated, the more it can go through.
The more light gets absorbed, right? Because we're measuring absorbance.
Right.
Okay, so what we say is that the darker a solution, the more light it absorbs. And that's true. That's why you wear sunglasses, right? Because they're darker and they kind of block out some of the light, right? They absorb some of the light. So for this copper 2 sulfate solution, we can actually go, oh, look, there's a connection between absorbance and concentration. Now, I also want you to notice for this very same solution you picked, I'm going to change the color of light. So that's kind of a brick red. Here's yellow. What do you notice happened to the absorbance?
It's a lot less.
It's a lot less. And so we can kind of play around with this. And I'm looking for at what point does it absorb light the best? And it seems to be at this brick red range. That seems, and we would call that its wavelength of maximum absorbance. So pick another color solution.
Is it drink mix a
Well,
solution?
I'll go the cobalt because it's red too. So,
Okay.
All right. Now notice before our greatest wavelength, our wavelength of maximum absorption was down here at brick red. But now I've got a different colored solution. So the old one's blue, this one's pink. So I would have to play around and find what wavelength it absorbs at the best. And if I cheat and use this preset button, it tells us. But you just should realize that for different solutions, you're going to have different wavelengths. So if you're going to be looking at a red solution, you don't want to use red light. You want to use a different color of light. And typically we say it's something that's, kind of doesn't contrast. What's that word? It's not the same color. It's a slightly different color. I'll think of it later. So complementary, that's it. A complementary color. So if you look at this graph, this is me shining a bunch of different wavelengths of light at something called Procyon fuchsia dye. What wavelength would you say it absorbs at the best?
At 550.
I love 550. So if we wanted to analyze a solution of this dye, I wouldn't use 400. I would use 550 because that is the most sensitive wavelength. So I would take my device and I would make sure we were reading at 550, right? But you can tell from the graph what is the wavelength of greatest absorption, right?
Right.
Okay, so this isn't bad at all. But if you've never seen this, these questions are horrible. But once you understand kind of what you're looking at, you're like, this isn't bad at all. Now, if I were to take a whole bunch of different solutions, like take your copper sulfate solution that you picked in the first place, and I picked out a bunch of different concentrations, and I measured the absorbance, then what you notice is, see how they kind of all line up in a straight line?
Yes.
Right? And that says the more concentrated on the x-axis you get, the higher the absorbance. So that's kind of like a positive slope right there. So if we develop that, if we take a bunch of knowns and plot a graph, then we can say, well, let's take an unknown. So I give you some unknown. You pop it in your device, right? You pop it in there and you're like, ooh, I wonder what the absorbance is. So you read the absorbance and you look it up on your graph and you go, aha, if this is the absorbance, then I can follow it down and I can find the concentration of the unknown. So anything that's a colored solution, you can do this with. People with pools will oftentimes, you can take your pool water and put it in a device or take it to a company. They'll add chemicals that make different colors, and then they'll pop it in the machine. And when they pop it in the machine, how dark it is tells you how concentrated it is. So it uses this very same idea of the darker it is, the more concentrated it is, and they can give you a very clear reading right away on, oh, this is how much chloride is in your water or whatever like that. So here's a graph. So let's see if, what would be the concentration at an absorbance of 0.5?
So at 0.5, it'd be around 7.9.
I love that answer, 7.9. And the AP world, you could be like, they'll probably take anything between 7.6 and 7.9, right? They're not gonna take 8, and they won't take 7 because obviously that's not it. But as long as you get in the right range. Now, what do you notice about all the dots?
Well, they're mostly just like they're not on the line exactly.
Right.
So it's an approximate line.
That's right. They drew a line of best fit because in the real world, rarely do the dots line up perfectly. So can you think of a reason why in this one right here, this thing right here, this dot, can you think a reason maybe why the absorbance was a little bit high? Oh, let me tell you how this device works. You take a little test tube type thing and you drop the liquid in it. You wipe it off to get off fingerprint and you stick it in front of a beam of light. So it looks kind of like this, right? So you stick your cuvette in and you got to make sure it's clean and you measure the absorbance. So can you think of a reason maybe why this one would be a little bit high?
Maybe the like the liquid that was smeared on it wasn't smeared as well or something.
Okay. So what if you got a greasy fingerprint on the tube and you didn't wipe it off? Do you think that would cause it to absorb more light or less light?
I think less light.
Okay. So now I'm talking about absorb, not pass through, right? So do you, if like I wear glasses, if I put a great big fingerprint on my glasses, it's harder for me to see because that oily fingerprint actually smudges the glass and it actually absorbs some of the light. So it's hard for me to see through it. So a greasy fingerprint might actually cause something like this to be a little bit higher than what you thought of. This one down here at the end, see how it's a little bit below the line? Well, what would cause it to have a little bit less absorbance? Well, you could name all kinds of things, like maybe you added too much water. What if when you were adding water to make your solution, you added too much? Well, then it would not be as concentrated. It'd be more dilute. And if it was more dilute, then the absorbance would go down just a little bit. And that's typically why we see lines of best fit, because no one makes a solution perfectly right every single time. See how that rolls?
Yes.
Okay.
So like
Yeah.
a thumbprint, a fingerprint, it would like increase the concentration.
It would look like it increased the concentration, you're right, because the absorbance would go up. It also could be because the person, whoever weighed out the solid, maybe that person weighed out too much solid. Or maybe they didn't add enough water. Anything that you can think of that would kind of cause a reason for why would that absorbance go up a little bit more than you thought it would. Oftentimes on the AP exam, they'll just ask you to kind of think about graphs and come up with a possible answer. But this calculation is actually on your equation sheet, so it's nothing you need to memorize or anything like that. But sometimes they might actually have you calculate the absorbance. All this other stuff, C is the concentration or the molarity. And then L and E tend to be constants because that test tube is always the same distance. So the L, the length of path traveled by the light, is this distance right here between them. You're not going to put in different sized test tubes. So typically that's a constant. And this value, this weird E looking thing, the epsilon, is something that they would have to give you. It's nothing that you would have to memorize or anything like that. But for copper 2 sulfate, it's always the same number. So it's not like it changes around or anything. And I can even do this. So watch the absorbance of our cobalt nitrate solution. Watch what happens when I make the tube wider. The absorbance goes way up because it has more of the liquid to go through. And if I made the thing skinnier, then you could see the absorbance go down. And all you have to do, you can do this at home, pour some colored liquid like apple juice or something like that, pour it in a really thin glass or pour it in a really container that's kind of wide. And you'll notice that one looks darker than the other just because the more light has to travel through something, the more the light gets absorbed. Right, so we kind of did this before. If the concentration was about 0.6, then, sorry, if the absorbance was somewhere around 0.6, you could use this graph to tell me concentration. So that's one skill you got to have. But if they gave you this, here's a frequency, could you calculate the wavelength if I gave you the equation?
Yes, I think so.
So you would run over to your formula sheet and you would go, oh, wait, I want wavelength. I'm given frequency. So I would go over and find this equation where C is equal to lambda nu. And then you would find this lambda thing and you would just plug in the numbers and notice that it says calculate the wavelength in nanometers. So if it wants you to do it in nanometers, then you got to find nanometers. If it just said calculate the wavelength, you could put it in whatever unit you want. But you know how FRQs with your teacher, sometimes they're very specific by what they want.
Right. So, like on an AP exam, would it matter if you did it? It's only the teacher.
Oh no, it depends. So it depends on the question, right? So in this right here, calculate the wavelength in nanometers. Well, it says nanometers, which means you have to do it in nanometers. If that part was out, if it had just said calculate the wavelength, then you could pick whatever you wanted to. But usually the AP exam is pretty specific with exactly what they want you to do.
Okay.
Mm-hmm. Right. So here it gives you this thing about ozone and that it blocks UV, which we're very thankful for, and that it has a frequency and it asks you to find the energy. So that's that other calculation I showed you where E is equal to H nu, where you take the H, which is a constant, and you multiply it times the frequency. So you could plug and chug that one, right?
Right.
Okay. Then it says the minimum energy necessary to break it is 387 kilojoules per mole. Now, this is 387 kilojoules per mole. This is one molecule of ozone. So do you remember how to calculate from moles of something to individual molecules of something?
Yes. Don't you just use the Avogadro's?
Yes, yes, you're so brilliant. Use Avogadro's number. So notice that they're trying to trick you in the question. So how much energy does it absorb per one photon? Does the molecule absorb per photon? Then in the second part, they're giving you how much energy for a whole mole of the thing. And so they're asking you to read the question and kind of pick it apart. And does it have enough energy to break the bond? So if we look at the answers, the first part is pretty straightforward. It's that E equals hv that we had talked about, and you get that much energy per photon. So we just get an answer, yay, we got a point. Then in the second part, it has you saying, well, that's how much it is for one photon. So if I use Avogadro's number, I can figure out what it would be for this many, for a mole of photons. And you get a final answer of 399 kilojoules. So notice the first answer is in joules, the second answer is in kilojoules, and I'm sure you've learned that you have to pay very close attention to units, right?
Right.
Now, here's the best part. As long as you found an answer and you compared that answer, you could say yes or no. So does it have enough energy to break this bond? Even if you had done the math wrong and you got 217. If you said 217 is less than 387, you could still get that point because you took your answer from before, even though it was wrong, and you compared it to the number given to you in the problem, which is great, right? Even though you made a mistake, it doesn't mean that the whole question is you're doomed.
Right.
Okay, so that's all I had for you today. So it's all about how do you make a solution? That was not bad. You can either do it by dilution or adding a solid. What glassware do you use to make a solution? And then kind of getting back in that mindset of light and what does light tell us about an atom? And I'm sure this is something you guys will practice in class. So before we end it, do you have any more questions?